In this video, we're going to be looking at the beta function. So the beta function is a function of two variables, and it's often defined as the integral from 0 to 1 of t to the r minus 1 times 1 minus t to the s minus 1 dt. Now it's possible to write this in terms of gamma functions, and one nice derivation is fairly similar to the trick for evaluating the Gaussian integral. So we start off in a way similar to how we found the Gaussian integral. We multiply the two gamma functions for r and s. So gamma of r is the integral of x to the r minus 1 e to the minus x. And then we have the integral of y to the s minus 1 e to the minus y dy. Okay, now we can combine this into a double integral. Okay, but this isn't great because, well, we can't really use polar coordinates very easily. We would need x squared and y squared in the exponent rather than x and y. So what we can do is say x equals u squared, y equals v squared, and then we end up with another double integral. Okay, so we get u to the 2r minus 2, but we have a 2u from the differential. So 2u to the 2r minus 1 times 2v to the 2s minus 1 e to the minus u squared minus v squared du dv. Okay, and this factor of 4 allows us to change the region of integration from the first quadrant to the whole plane. So what we can do is just write this as the integral from negative infinity to infinity, negative infinity to infinity, of absolute value of u to the 2r minus 1, absolute value of v to the 2s minus 1, e to the minus u squared minus v squared. Now we can use polar coordinates. So I would say u equals r cosine theta, except I've already used r. So I guess I'll use rho. And v will be rho sine theta. Okay, so now theta is going from 0 to 2 pi. Rho is going from 0 to infinity. And I have absolute value of rho cosine theta to the 2r minus 1. Absolute value of rho sine theta to the 2s minus 1, e to the minus rho squared, and then I have an extra rho from the Jacobian. Okay, so it looks like a mess. Well, it is a mess, but quite a lot of it simplifies. So we can separate out the rhos and the thetas. So for the thetas, I have integral from 0 to 2 pi, absolute value of cosine to the 2r minus 1, absolute value of sine to the 2s minus 1, d theta. And then for the rhos, I have rho to the 2r plus 2s minus 1, e to the minus rho squared. All right, now this first integral I'm going to write as 4 times the integral from 0 to pi over 2 of this. So this I can do because of the symmetry. And now I don't need any absolute values. Okay, and then what is this integral for rho? Well, it's a gamma function, not surprisingly. So I make a substitution for rho squared. So for example, if I say w equals rho squared, then this will be the integral from 0 to infinity of w to the r plus s minus 1/2 e to the minus w. But now the differential is 1 over 2 root w. Okay, so the exponent in this integral is really r plus s minus 1. And so I have 4 times this integral for theta. And then I have half the integral of w to the r plus s minus 1, e to the minus w. Okay, and that's exactly gamma of r plus s. So finally, this shows that gamma of r, gamma of s equals, I combine the 4 and the 1/2, 2 gamma of r plus s times that trigonometric integral. So if I want, I can isolate that integral. And I get gamma of r, gamma of s over 2 gamma of r plus s. Okay, now this is almost the beta function, except I don't want any trig functions. So what I'm going to do is say t equals sine squared theta, and then dt is 2 sine theta cosine theta d theta. Okay, so the integral then becomes, I'm going from 0 to 1, and then I have, well, I need a sine and a cosine for the differential. So it's really cosine to the 2r minus 2, which is 1 minus t to the r minus 1. And then t to the s minus 1. And then I have a factor of 1/2 dt. Okay, finally, I cancel the factors of 1/2, and I get the beta integral that I want. Well, okay, flip r and s. So the beta function is the integral of t to the r minus 1, 1 minus t to the s minus 1, which is gamma of r, gamma of s over gamma of r plus s. Now this gives us another way of computing some values of gamma. So for example, if I want to compute gamma of 1/2, I can let r and s be 1/2. And I get the integral of 1 over root t times 1 minus t dt. Now if I go back to the trigonometric form, this is twice the integral from 0 to pi over 2. Now remember, it was cosine to the 2 times 1/2 minus 1, so that's a 1, times sine to the 2 times 1/2 minus 1, which is 1. Okay. Now that is pretty clearly just pi. Okay, so I get gamma of 1/2 squared over gamma of 1, which is 1, equals pi. And this also allows me to compute some other pretty wacky integrals. So for example, if I have the integral from 0 to 1 of t to the minus 3/4 times 1 minus t to the minus 1/4, well, that's beta of 1/4 and 3/4. So it's gamma of 1/4, gamma of 3/4 over gamma of the sum, which is 1. Okay. And now we had this reflection formula. Gamma of z, gamma of 1 minus z was pi over sine pi z. Okay. So we get pi over sine pi over 4, which is pi root 2. Okay, so we end up with the integral from 0 to 1 of 1 over the 4th root of t cubed times 1 minus t equals pi times the square root of 2.